failed. Well, yeah, do you want our memo while I? So our second speaker is Cynthia Rush from Columbia, and she's going to give another awesome talk on information theory and statistics.
Okay. So today I'm going to talk a little bit about variational inference and robustness. So in particular, the robustness of α-Posteriors and their variational approximations to model misspecification. So, all right, so just a quick overview. So today I'm going to study the α-Posterior. So this is just our normal posterior, right? Kind of proportional to the likelihood times the prior. But now the likelihood is scaled by an alpha factor that's going to be some value in 0, 1. So we're going to study these objects, the α-Posterior that I denote like P sub alpha, and also variational approximations to the α-Posterior, right? So the closest distribution and some simplifying set, in particular the Gaussian mean field, in terms of KL divergence. And so there's been a lot of work, a lot of recent work analyzing statistical properties of these procedures, and we're just trying to contribute to this literature by showing that these procedures, when they're properly tuned, have some robustness, some rigorous sort of robustness properties to misspecification. So that's kind of like the goal for today. So this is joint work with some of my colleagues, Marco, Pepe, and Amilcar. Marco's in stats at Columbia with me. Pepe and Amilcar econometricians. Okay, so first I just wanted to say a few words about variational inference to make sure we're all on the same page and sort of set up some of my notation. Okay, so the idea, right, is that you know, we're thinking about doing posterior inference. So what does this mean, right? Well, I've, you know, usually a common thing to do, right, is we put some sort of probabilistic model on our data. So we get, this is, you know, something we think of as a joint distribution over the data, which is, you know, my observable X, and then also some hidden or latent variables, theta, right? And then the idea is kind of, we want to use the data to learn something about theta. And then, you know, we interpret theta as telling us something about, you know, the scientific world or whatever problem we're studying. Of course, right, you know, what we would like to do is just look at this posterior distribution, right? And, you know, use that to say something about theta. But in general, when the problems are complex, actually calculating this posterior distribution is very difficult, right? So in particular, finding this marginal usually involves like a high dimensional integral, and you can't do it. So, you know, what people do, right, is they in some way try to approximate this posterior distribution. So one way you might approximate it is to try to sample from it using MCMC. Another way, you know, which we're going to look at is variational inference, which, you know, in MCMC, you might think of it turns posterior inference into sampling. Variational inference turns posterior inference into optimization, right? Okay, so right, this is what variational inference does. So this is an image I stole from Dave Bly's NeurIPS tutorial back in 2016, right? So the basic idea is that, you know, we'd like to access this posterior. We can't, because we can't calculate the marginal. What I'm going to do is just find an approximation to it, you know, that minimizes the KL divergence, where this approximation comes from some simplifying, like, you know, some set of simple distributions. So the first step is to just posit this variational family. These are our simple distributions. These are going to be, you know, something, some class of distributions over these hidden variables. So in the image, right, I have my true posterior is up here. My like oval here represents my simplifying class, right? What I want to do is try to, you know, my simplifying class is going to be parameterized by nu. So my goal is to find the nu that minimizes this KL divergence, right? And we usually do it with some sort of algorithm that updates our approximation. That's the kind of squiggly line, right? So, you know, what do, right? The variational parameters that we select, this is our approximating distribution, are going to be those that minimizes the Kullback-Leibler divergence. Okay, So what we want to do is think about the robustness properties of variational inference. So robustness, what I mean today is robustness to model misspecification, right? So the basic idea is that we want to say something about how well variational inference performs, even if the assumed model is wrong, right? So that joint distribution I put over my data and my hidden variables. Often this is wrong, right? It's usually a simplifying kind of view of the world. So how do these procedures perform in that case? So again, you know, we're looking at, in particular, the alpha posterior and its variational approximation. So what I'm going to study today is just a variational approximation that's in that takes as a simplifying set the Gaussian mean field. This is, you know, a commonly used sort of variational family, and it's also in some sense the simplest. It just means I'm going to think about my hidden variables as being independent, and I'm going to give each of them their own Gaussian distribution. So sort of what we want to estimate here is for each of these theta values, I want to get a mean and a variance, right? So that's the idea. So okay, these alpha posteriors have many names in the literature. They've been called tempered posteriors, fractional posteriors, power posteriors. It's also a Gibbs distribution. You know, these have been studied for a long time. Perhaps going back even to, you know, the 90s with the work of Vovk and Barron and Cover, who, you know, had these sorts of ideas that we can enhance Bayesian procedures by, you know, somehow decreasing the influence of the likelihood. And so, you know, okay, so people have been thinking about these alpha posteriors for a long time, and there was like sort of a resurgence of interest maybe in the like early 2010s when folks started empirically seeing some nice robustness properties to you know, of these alpha posteriors. And so you know, there's been some recent work on these things, but it's often, you know, sort of in you know, high dimensional settings or non-parametric settings, or it's mostly empirical or heuristic in some way. So kind of our first goal when we started this project, which is what I'm going to show you today, is you know, we wanted to just see if we could say something rigorous about the robustness properties in kind of our like very standard statistics setting, which, you know, is parametric and low dimensional models. So low dimensional, I just mean I'm thinking about, you know, my data is you know, amount of data is growing, but the dimension of that theta vector, the hidden variables, is fixed, right? Okay, so now I'm just going to kind of define, you know, what I mean by this model misspecification, right? So we're thinking about, you know, modeling our data through a parametric family of densities, right? So this is just going to be this class cursive P, right? And so if, you know, the true data generating process is in the class, then the class is correctly specified, right? So if I think of P naught as the sort of true data generating process, if P naught is in this class, we're correctly specified. But if it doesn't belong to that class, we are misspecified, right? Okay, and then you know, the other sort of notation I need is the maximum likelihood estimator, right? So this is, nothing is like surprising here. This is the usual definition of the maximum likelihood estimator, right? I'm thinking about, you know, it being defined with respect to my model class P that may or may not be correctly specified, right? And we're also going to assume uniqueness and asymptotic normality of the MLE. So we're basically just doing this because, you know, we would like to say something rigorous about the robustness properties, and, you know, we want to kind of emphasize that, like, this is not some edge case where you get robustness just in like when things are going as planned, you know, you kind of get robustness. So the idea is here, you know, we're in this usual setting where things where things you know, perform and kind of in the way they should. So when we think about asymptotic normality of the maximum likelihood estimator, it's going to be centered on some theta star, right? Where this theta star depends on like whether or not my model class P is correctly specified, right? So if it is correctly specified, then of course theta star is going to be the theta that generates the data. But if it isn't, then this is just going to be my pseudo true parameter. So it's the one that's closest to the truth in terms of KL divergence, right? Okay, so kind of the first thing we wanted to sort of study were just what are the asymptotic properties of the alpha posterior and its variational approximation. So in general, in statistics, we know that for like a wide class of models, right, the posterior, even under model misspecification, is asymptotically normal. And so the first question was like, all right, well, if we just throw the alpha in there, does that change anything? How does it change anything? And, even though we kind of thought that this might be something that exists in the literature, apparently it didn't. So our first test was to just try to look at these sorts of Bernstein-von Mises results for alpha posteriors and their variational approximation. So Bernstein-von Mises just means kind of, asymptotic distribution of posteriors. So in particular, the first thing we did was kind of extend to existing results on asymptotic normality of posterior distributions and variational approximations under misspecification. So in particular, for standard posteriors, so like this is like alpha equals 1 posteriors, right? There's a classical result by Klein and van der Vaart that gives us asymptotic normality under misspecified models. And more recently by Yishen Wang and Dave Bly, there's asymptotic normality results for variational approximations under model misspecification. So our first goal was to extend these, when we study the alpha posterior or the variational approximation to the alpha posterior. So I'm going to say that I'll use the term asymptotically normal, but it's a bit of a, I'm being a little loosey-goosey with my language here, right? So what I actually mean is that the total variation between the alpha posterior or its variational approximation and a Gaussian distribution, which also depends on n, right? That total variation goes to 0. So that's what I'm saying there. Okay, and so what we were able to show is that in both these cases, so for alpha posteriors and for the variational approximations to the alpha posteriors, we still get the asymptotic normality. So first, I'll just quickly state some assumptions, and so the first thing we want to study is the asymptotics of the alpha posterior itself. And so it turns out that we just need the same assumptions of Klein and van der Vaart to get the asymptotic normality. So in particular, this requires some assumption about the local asymptotic normality of the model, and also an assumption about the rate of concentration of my alpha posterior. So while these are, okay, in the statistics community, I believe that these are probably about as general of assumptions as we're going to get for asymptotic normality under misspecification. If you want to think about, extending these results perhaps to like Bayesian neural networks or something, we're excluding that here, right? So in particular, like I'm assuming identifiability and stuff that doesn't exist for the Bayesian neural network. So while these are, if we want asymptotic normality, I think this is as general as we get. I think, what we'd like to do is extend this perhaps to more general models, but I think there we won't actually get the normality. This future work is if we want to study kind of robustness of more general Bayesian models, what do we do? But for now, these are kind of classic statistical assumptions. So in particular, something like this, right? If the data is assumed to be IID, then it basically just requires that you have like a second order Taylor approximation, or at least that's a sufficient condition. So it's fairly light. And so, Okay, so the first result is that, under those assumptions, we can show asymptotic normality in the sense that the total variation distance between our alpha posterior and a limiting Gaussian approaches 0. And so the interesting thing here is that, okay, so the Gaussian, so the only thing that the alpha changes here, it doesn't change the mean. So the mean of the limiting Gaussian is still the maximum likelihood estimator. But what it does change is it scales this variance, right? So here, the V theta, this is like an inverse Fisher information matrix, right? So it tells us something about the curvature of our likelihood at the pseudo-true parameter. So what we've done now is, right, alpha is a value between 0 and 1. So we've sort of upscaled the variance here. So there's a few ways, I guess, to interpret it. One would be like, if you throw the alpha onto the likelihood and the posterior, this is basically saying that when we think about asymptotics, it's like we now have in alpha data points instead of in data points. So this is sort of slowing down the concentration by spreading out the mass. Okay, so the only way it changes the asymptotics is through upscaling the variance. Okay, so we want to play the same game with the variational approximation too. So now, what do we what are the asymptotics for this variational approximation to P alpha, and kind of like you can guess what's going to happen, right? So the sort of idea is, if I know P alpha limits to this Gaussian, if then I kind of project P alpha onto the Gaussian mean field, its limiting Gaussian is going to be like the original one projected onto the Gaussian mean field, right? So, okay, so basically what this says, right, is, this is the object we'd like to study. It's the Gaussian mean field approximation to P alpha. And so it's going to limit to basically the sort of density in the Gaussian mean field that's closest to the original limiting Gaussian distribution. So basically all this does is, now we've kind of diagonalized the variance here, right? This is what sort of the Gaussian mean field requires us to do. There's a slightly more conditions here, but I'm not going to go into too many details for this talk. Though I will mention, in some sense, kind of something we know about like Gaussian mean field variational inference is it underestimates the variance, right? So the fact that we've kind of upscaled the variance here is in some sense, I think the right idea. This is a nice thing because, one of the issues with the variational inference here is that, you sort of are underestimating the variance always, which is like kind of bad. You don't want to you don't want to be more sure than you are. So here the alpha helps in that way. Okay, so now using these asymptotics, we'd actually like to study the robustness. So okay, the first kind of question was, how do we measure robustness to model misspecification, right? So what we'd like to say are, or what we'd like to answer, right, is, are the alpha posteriors or their variational approximations more robust in some sense than just standard Bayesian inference? So kind of alpha equals 1 Bayesian inference. So the first question is, how do we measure robustness? And so the idea that we studied, which we believe is due to Gustafsson, is to use the KL divergence, right? I'm an information theorist, so like why go too far away from like the things I know and love, right? So the idea, right, is we have two different procedures that lead to incorrect posterior inference, right? Procedure A, procedure B, they're both wrong, perhaps due to model misspecification or limited computational resources or whatever. We're still going to say one procedure is more robust than the other if it's, closer to the truth in terms of KL divergence. So even though they're both wrong, we can still kind of preference one if it gets us closer to the truth. So the object that we'd like to study is, this closeness in terms of KL of the objects we're considering to the correct posterior. So in particular, I'm looking at the KL between the correct posterior and the reported, where the reported here is like either my P alpha or my Q alpha, that variational approximation. Okay, so all right, so to enable like the tractability of studying this object, we aren't going to assume that our model class is always misspecified or always correctly specified, but rather that there's some sort of probability epsilon that could change with the amount of data, some probability of misspecification epsilon n. So I'll say a little bit more about this when I'm interpreting the results, but kind of the short story is if you always assume that you're misspecified, then the results say then, well, okay, alpha should be 0. Don't use the wrong likelihood in your analysis. If you're always correctly specified, alpha should be 1. Obviously, use it because it gives you information. So somehow, like the interesting regime where sort of our phase transitions occur, is this where there's some probability of misspecification. So, what I said, right, is that I wanted to study this, right? But now if there's some probability of misspecification, right, the meaning of P correct is going to change according to whether I'm misspecified or not. So what we study are actually like expected KL divergences, right? One with the misspecified contribution and one with the correctly specified contribution. So again, right, what this changes is the meaning of P correct, right? So the correct, okay, if we're well specified, right, P naught is in my cursive P model class. So P correct is simply P alpha with alpha equals 1, right? It's the true posterior. If I'm misspecified, I'm thinking of P correct as being some P star, which I'm going to think is, sort of coming from some parametric model for the truth. Kind of the important thing here is that, the thetas in my original model still have some meaning in this other space. But now we've also put some gammas here. So in truth, right, this could actually be non-parametric, like gamma could be infinite dimensional, but we still have to have some meaning of theta in the misspecified case. And so, okay, so the object we'd like to study is then this. So if we're thinking about robustness of alpha posteriors, what we'd like to study is this expected KL. So the first term is my misspecified contribution, right? So it's the KL between, my reported thing over here, then the truth over here, but I'm misspecified with probability epsilon. So the truth is this P star that comes from my other sort of model class. And then with probability 1 minus epsilon, I'm correctly specified. My truth now is alpha equals 1 posterior, right? So the idea, right, is that, okay, so this is how I'm measuring robustness. So what I'd like to do is find the alpha that minimizes this expected KL divergence, right? So the alpha posteriors for the alphas giving smaller values of this KL, this is saying that inference procedure is getting us closer to the truth. So we're more robust to misspecification. And of course, I want to play the same game with variational approximations. So what I've done here is just replace, P alpha is my actual alpha posterior, Q alpha is the variational approximation to it. Okay, so these are the things I'd like to study. The problem is it's hard, if we're thinking about n being finite. So what I'm going to study instead are kind of the asymptotic versions of this, right? So I have, my BVM theory in my back pocket. So now is where I'm going to use it. So instead of studying this, finite n sort of thing, what I'm going to do is replace, these posteriors with their sort of their limiting Gaussians, right? And so now I've put myself in a really good situation because I know exactly what the KL divergence between Gaussians is, right? So, what I'm going to do now, right, is study this object. And again, this is something that I'd like to minimize with respect to alpha. And then whatever the minimizing alpha is, this tells me like sort of the alpha that gives me the most robustness. So I'm going to define, R alpha as this expected KL for my alpha divergences, or sorry, my alpha posteriors, and then R tilde alpha is just going to be the same thing, but for the variational approximations, right? And then my goal is going to be optimize R alpha, R tilde alpha with respect to alpha to find the, the most robust procedures. Okay, so right, this is what I'm trying to find. You all believe me that I can do this, right? We know the KL divergence between Gaussian distributions, and so these are the results. So basically, what this says is if we study the optimal alphas, we find, at least asymptotically, that these are going to be values strictly less than 1, right? So this says that some tempering of the posterior, in fact, gives us the most robust inference procedure. And so in particular, these things depend on, this difference, theta naught minus theta star, which is like the magnitude of misspecification, right? So this is kind of like how wrong the original model is. So, I mean, while this is like intuitively something that the alpha star should depend on, and, as you get more wrong, more misspecified, this says alpha should be smaller, you should kind of downweight the likelihood more. In practice, right, this is something that's like hard, or if not impossible to know, right? So, while this says that, while this does give us some rigorous sort of guarantees for robustness of these procedures, it doesn't actually suggest what we should do in practice. So that's just one limitation of the result that I'll talk a bit more about when I say something about future work. But okay, I just wanted to end by some sort of implications of this result that I think are interesting. So in particular, what this allows us to do is compute the limit of these optimized KLs. So if you plug in the optimal alphas, you can look at the KLs that tell you the sort of the distance from the truth. And so, the interesting thing is that, when we plug in the optimal alphas, both of the terms increase logarithmically in the magnitude of misspecification. But if you go to alpha equals 1, so if you say no tempering of the posterior, then these KLs will increase linearly in the magnitude of misspecification. So the tempering, right, says that the way that you kind of zoom away from the truth in terms of KL is a different like magnitude if you do some tempering here. I'll also say that under some conditions that we can characterize, optimized variational approximations to the alpha posteriors are actually more robust than the optimized alpha posteriors. So I was sort of surprised at first that you get additional robustness with the variational approximation, but kind of, upon some reflection, perhaps I shouldn't be, right? So it's like, in some sense, we know that if you just smooth things when you estimate, right, that can give you some sort of robustness. So what we're doing with the Gaussian mean field, approximation is simplifying, is smoothing in some sense. So it's not surprising that there are some settings where this helps you out. So, kind of like my sales pitch, right, would be that this perhaps provides a rationale for using variational inference due to its robustness properties. On top of, usually people use VI because it's computationally very nice, especially, compared to MCMC. But we also get some nice robustness as well. So I'll just, I'll end by just saying a few kind of open questions, right? So in particular, I think a big question is like, how do you actually select alpha in practice, right? So I gave some theoretical results that like give me nothing to say to practitioners about what to actually do, right? And so that's not great, and we'd like to have something that we could suggest to do in practice. And so we're starting to work on this with my student Ruchira, who is going to give a poster tomorrow. So she's looking at if we select alpha in a data-driven way, what does this sort of tell us, right? And so one of the reasons that this work, data-driven alpha doesn't apply here is that if you use data to select alpha, then alpha is going to change with n as well, right? So you need some more tools to kind of study what happens there. So come to the poster if you're interested to see what we've done so far. And then as I mentioned earlier, right, these are kind of, these results rely on the asymptotic normality pretty heavily, right? And so the question would be, if we want to go to more complicated models like Bayesian neural networks, right? How can we play the same sort of game, right? And so there, the asymptotic normality isn't going to be there. There are some asymptotic studies, but the limiting distributions are more implicit in these sorts of things. So a kind of open question is like, what can this say in sort of the Bayesian neural networks, or what can this style of argument say in the Bayesian neural networks world? So I think on that, I will stop and take a few questions.
I love this idea of like the epsilon n, but it was a little bit, so I guess it still says with some probability I'm good, right? What if you had this sort of idea of building these models somehow from a class that becomes gradually better?
Yes. Okay.
So would you get similar?
Yeah. Okay. So I didn't give you all the details about the epsilon n because it's complicated. So in fact, what we need for these results to make sense is that epsilon grows kind of like a constant over n. So what this means, is that ultimately my epsilon is the probability of misspecification. So as your data grows, you're becoming more and more sure that you're correctly specified. And so I will mention that this is a non-standard model for misspecification. We went back and forth with the reviewers for a minute about this, but I'll give you a pitch for why I think it's at least reasonable, that you should become more sure as you get more data. So I think the idea we're imagining is kind of, we have a really careful modeler who has invested a lot of time and energy into finding a reasonable model, but you still have to acknowledge that there's some chance that it's wrong. And so the fact that you could get more sure with more data, right? This seems to be reasonable based on like sort of the idea that we believe in model checks based on the data, right? So we should also believe that if we get more data, we're more sure. Yeah. So the question, I guess, is like, what happens if we're not in this regime in some sense? Or
no, I was thinking that maybe there are other ways to interpret it. The easy one, like if it was Gaussian, so I'm like increasing the resolution of the models, and sort of I have instead of this probabilistic interpretation, I have some complexity. And I was wondering if you think the mathematics will work there, because also it's nicely, it's what practice talks about.
yeah.
So like if the model, the class of the models that you're considering are becoming richer because n is growing, then will you be able to sort of replicate this? I mean, I love it.
Yeah. I'm thinking
what happens. But I think it's very powerful, and I.
Yeah, I mean, at some level, my deep down, my feeling is that, this is perhaps not exactly the right way. And I think that perhaps, maybe what you're suggesting, I think that would be willing to at least explore the same sort of analysis in the way you're suggesting. It's not obviously not going to work or something, but yeah. I mean, there's still some, we're still thinking a lot about what the correct notion of misspecification actually is. I guess it's my short answer.
I'm going to make a comment while I
Sure.
let Raphael set it up.
Oh, yeah, sure.
There's some connection between this and this kind of robustness in machine learning where I give this alpha can correct from, you start with one space and you're actually mapping back to another space. Within some bounds, it can do it for very simple models. A bit complicated if the dimension of that data is very, very tough. We'll talk about that.
Yeah, no, I think it's, I think there's like a lot of directions to go here, and we're.
So what I want to ask you is alpha star a function of X, which it should be? Like, because X is your data, there's an underlying model on it.
Well, so it's not a function of the alpha star.
Okay, should
so
be
the
giving a
alpha-
point-to-point mapping back.
Yeah, so the thing I showed up there was asymptotic, so ends to infinity. But we have alpha star finite will be yeah, so it will be a function of the data, but it's a little bit the finite n alpha star is like implicit in some sense. So like this is why we present the asymptotic version, because you get like a clean sort of, or, something interpretable. But yeah.
Thank you. Our last speaker for this session is Raphael Oliveira. Do you